Welcome back to Principles of Engineering. Today we're looking at our truss analysis, and we just got done analyzing at point E. So now the next step, what we're going to do is we're going to look at point C. And again, we're saying that if point C is not moving, we can reason that is not moving because the overall truss does not move. So because the truss isn't moving, C isn't moving. So when I draw point C, I get the point itself, and then I will be able to put two vectors in here that we don't know the value for yet. And this is going to be represented by the force BC. This is going to be the force from C to D. And this force we actually already know. It's the force from C to E. And we found that already. We found that in our prior step, and that is equal to 500 pounds in tension. So right here, it's 500 pounds in tension. So let's go ahead and write that value in here. That's the reason I drew the arrow going down. That's the symbology for it being in tension, as you recall. So remember the premise. If the overall body isn't moving, so this entire truss is not moving at all, so it's not moving back and forth, up or down, or rotating, this point cannot move either. Point C cannot move. So by saying it's not moving, we can say the sum of the forces in the x direction has to equal to 0, and the sum of the forces in the y direction has to equal to 0. Furthermore, we know, because of the math behind this being 2 feet, we know the relative angle here is 45, and this one is 45 also. Not that we need both of them, but we know that going into it. So let's talk about this case, the first case, and the first case is going to be looking in the y direction. So the summation of the forces in the y direction have to equal to 0. I can break my vector FCD into a component that goes in the x direction, FCDX, and a component that goes in the y direction, FCDY. So I'll draw that in a little bigger scale here. But it's important for us to understand that concept, because what I really have at point C now is I have got a vector that looks like this, FCDY, and a vector that's added to it, FCDX. And now I can put in here my FBC, and I can put in my FCE. So this 500 pounds is in tension, or it's pulling down. So now we can look at this and it's a little bit clearer, and hopefully you can see how I did that. I broke my vector FCD, which runs right here. I broke that into the individual units. Now we're not real sure if it's in tension or compression, but right now we assumed tension. So if I come in here and try and solve this, let's start out by solving in the y direction. And I'm going to say the summation of the forces in the y direction equals to 0. So from my diagram, I have FCD y component plus FCE has to equal to 0. Now I know FCE, and that's 500 pounds, using our conventions up here. It's a negative 500 pounds, so I can say FCD y plus a minus 500 pounds equals to 0, or FCDY equals to 500 pounds. Now, holy smokes, I got plus 500 pounds. What's that mean? It means that FCDY, redrawn in red here, is actually going up, not going down. Going up. What that also means is, hey, this one's got to be reversed in order to make the vector math work out right. That's all that that means. So I've redrawn my vectors here. So up. Now we know that I've got a situation where I've got a vector. It looks like this. I've got an x component and a y component. F, C, dx, F, C, dy. I've got 45 degrees in here. And I've got F, C, D. Now, as you remember, the sine of theta equals to the opposite over the hypotenuse. Looks like we could find the hypotenuse, which is in fact FCD. So FCD is my hypotenuse. We could solve for that and say that the hypotenuse times the sine of theta equals to the opposite. Or my hypotenuse equals to the opposite divided by the sine of theta. And then that equals to 500 pounds. And that 500 pounds is up. So 500 pounds plus 500 pounds divided by the sine of 45. If you punch that into your calculator, you will get 500 divided by 45. Sorry, I had to find my mouse. Sine equals to 707 pounds. 707 pounds. Oops. Use the right end of my pen here. All right. So, what did we figure out now? Well, what we said is we can say that this is going to be 707 pounds, and I can come in here and update my force diagram and say it is 707 pounds going up. There we go. And I'm not going to worry about the 0.11. Now that's 707 pounds right here, 707. This would be in compression because it's pushing against the point. So I'll come up and label my overall diagram. Not 7,007, but 707. And that is in compression. Super. So we're almost done with E. Got a little bit more work to go. So let's go ahead and look at E again. And I said that was 707 pounds in compression. And I'm still at my point E. Or point C rather. Here it is. So now what I've got is I've got a vector going in this direction, 707. I've got a vector coming down, 500. And now I've got an unknown vector right over here, which is my force, BC. So similarly, when we looked at this vector, which was the force from CD, so I'm just going to draw the force at BC and then the force at CD, compression, and remembering that I can break this into an X and a Y component. So I'll come back here. And this is FCD, and here we have FCDX, FCDY. So in our X direction now, you can say the summation of the forces in the X direction has to be equal to 0. Otherwise, my point C would be moving. So what do I have in my X direction? I've got FCDX plus FBC has to equal to 0. Well, the question is, what is FCDX? We know that, again, the same unit triangle that we had before, this being 707, that being 500, this is 45, we could either use Pythagorean Theorem, which just says a squared plus b squared equals to c squared, and solve, because right now what we have is a and c, or we could use the relationship that says the cosine of theta equals to the adjacent divided by the hypotenuse. Either one of those we could solve and find the adjacent side. So this would translate to, say, my hypotenuse value times the cosine of theta equals to my x value, FCDX, which would then be 707 pounds times the cosine of 45. Or I can come over and say that I'm trying to find b squared. Come over and say that a squared plus b squared, or 500 squared plus b squared equals to 707 squared, or b squared equals 707 squared minus 500 squared, or b equals the square root of 707 squared minus 500 squared. Either one will solve the equation for me. So let's go through, and I'll use the trigonometry because that's a good skill for you to have. So if I just go 707 times 45 cosine, lo and behold, it equals 499.9. It equals 500 pounds. And that's kind of to be expected, isn't it? Because we've got a 45-degree angle here, right? So we would expect 500 and 500. Now our sign on it is positive, or it's to the right. So 500 pounds to the right. So why did we do all that? Well, we've come back up here and we just said that this is 500 pounds plus FBC equals to 0. Therefore, FBC has to equal to a minus 500 pounds, or left. So we look up at our vector, we did draw that left, and this is 500 pounds. What's that mean? It puts the member into tension. So going back to our force diagram, we can now put 500 pounds tension in there for the element from BC. So hopefully that all made sense. We're going to move on and pick up the pace here a little bit and use point B next.